speaker here is Jonathan Weinberger, who's going to tell us about the dependent Gödel fibration.
Thanks very much for the introduction. Can everyone hear? Yeah. Okay, so I'm going to talk about joint work in progress with David Prota and Valeria Tyler. So David is also in the audience here. Valeria is not. Let's start off with a little bit of history. It all goes back to the 50s when Kurt Gödel in the Philosophical Dialectica journal published a new proof interpretation or proof translation in order to do a consistency proof of intuitionistic arithmetic via translating the formula of this system into a new theory called Gödel state, which is a quantifier theory of finite type functionals. What this means on a technical level is not completely relevant for us now, but there are a few key features that will be kind of the red thread in this talk. So let's look at the, first of all, what is the idea? So the overall pattern of this translation is that we have given a formula in this Heiting arithmetic, and we're constructing a new formula, phi upper d, of the form there exists x such that for all a, y lower d is true, and these formulas are defined in some inductive way. So one key feature in this translation is that all the target formulas will be of the form there exists, and then for all, and then some formula. And so this is the person who we owe this big step, and this is the article. If you want to take a look, it's really available on the internet in German. I'm not sure about any translations, but anyway, you can find it there. How does this translation look like? So we don't want to go through all the steps and details right now, but as I said, we're basically translating formulas phi and psi into this new format with these alternating quantifiers here. So if we're given an atomic formula, the interpretation does nothing. For conjunction of two formulas, we kind of straightforwardly apply the conjunction onto these kernels here of the individual formulas. Because we're in an intuitionistic theory, when we're doing a disjunction, we have to add witnesses for each of the members of this disjunction. That's kind of what happens there. So here's already a little typo. So when we're translating universal quantification like this, of course we want so basically we want to make these witnesses functional, so we have to introduce a function x, so that for all should be, and there exists big X such that, and then this function witnesses the truth of phi at each step. So the case for existential quantification is more or less clear too. What is kind of the most remarkable step is the translation of implication, which is this expression here. And one intuition how to read that is as follows. So we're introducing two functions or functionals here, u and y. And so u is just, u just keeps track for any witness x of phi. We want to have a specified witness ux for the truth of psi. So if x witnesses the truth of phi, u of x witnesses the truth of psi. And then for any counterexample to psi, let's call it v, we want to have a function that witnesses also that phi is not satisfied. So that's the intuition for this interpretation here. I mean, to really see what's going on, it's kind of a bit more involved to work this out, but something we can take away from this, because it will play a role in all these categorical constructions that are to come, is that we kind of have a forward and a backward function. U and Y. So as the saga continues, as follows. So Valeria de Paiva in her 89 PhD thesis introduced the categorification of Gödel's dialectica interpretation, where she lifted this to the level of categories by assigning to any finitely complete category C and a new category called the dialectica category of C. Some uses that she explored in her thesis and in later work were variations and complications of this involving monoidal structures, giving models of linear logic. More pertinent to the topic of the day is work by Hyland, who devised a categorical way of doing proof theory via a dialectical construction on the level of fiber preorders. There's a bunch of authors that looked at topos theoretic versions of dialectica, and Gödel in her PhD thesis 6 years after Hyland defined the dialectical construction on the level of Gödel fibrations. And there's a very nice account of Hofstra where he characterized dialectica fibrations as certain bicompletions, doing some two-monad theory there. Very nice paper, the dialectica monad and its cousins. So he did the case of what you could call simple or non-dialectical fibrations, which a generalization thereof will play a role in this talk as well. But this is some of the important groundwork. There's been some comprehensive follow-up work by von Gleyn and Moss in their PhD thesis and the Wicks paper on polynomial models of type theory that also use and generalize these dialectical constructions. And there's another polycategorical version of dialectica due to Schumann. And the story goes even further, so there's definitely some more examples. So some of which you can list here. I mean, very hot topic at the moment in applied category theory is categorical systems theory, about which David talked on Monday. So there are also some connections there. What I want to mention is last year there was an AMS math research community on applied category theory with a project on dialectica mentored by Valeria, and you can read some summary by her on the Topos Institute blog post. And as a follow-up, there was a special session at the joint math meeting with many talks from our project, and I want to highlight Matteo Capucci's talk on exactly these vibrational dialectical constructions and their connections to optics and lenses. So these are some photos from last year. You can see very happy people here, and they're very happy because they got to think a lot about dialectica. So our work that I'm talking about today is a generalization of a project by Davide Trota, Matteo Spadetto, and Valeria, where they introduced the notion of Gödel fibrations and showed that those coincide with dialectica fibrations. So Gödel fibrations are some kind of bicomplete vibration with enough quantifier objects, and a priori it's not so clear that these notions coincide, and it's kind of non-trivial to show that, and that was one of the major achievements of their work. And the interesting thing is that that this notion of Gödel fibration gives a completely intrinsical definition of this notion of quantified freeness. So what this characterization theorem shows is that dialectica, which you can see as a kind of completion, which is like an external process that you apply to a category or a fibration, coincides with something that is completely intrinsically defined, namely this Gödel fibration via quantifier-free objects. And so what we're doing with David and Valeria in the current work is we're generalizing this construction to dependent version of dialectica. and prove this expected equivalence. And also we have as a parameter a choice of maps in the base category via the class of display maps, so you can kind of parameterize with the class of maps with respect to which you want to be complete and co-complete to. And one kind of informal way, or first step to say what is going on is the following. So the previous work in the non-dependent case was dealing with these maps of the form, just simple product projections, where we're looking at arbitrary general maps, U over some base types X, which you can see as type families U parameterized by this base type X. And so that means there is a whole range of generalizations going on. So prior we had these, we had like existential and universal quantifier, or product, simple product, and simple functions. Those are each subsumed by the dependent sum, the sigma type, or the dependent product, the pi type, respectively. And those each can even be seen more abstractly as versions of co-partition transport and this kind of push-forward transport in a bifibration or trifibration with this other adjoint on the right. So to do a little whirlwind tour on this classical dialectica category, what does it look like? So the objects are, so that's already the dependent version. So the objects are given by arrows from U to X, as I just said, together with the predicate. So it's an object on U, and you should think of this as these objects that are kind of like our formulas that are output by the dialectic interpretation, namely objects of the form there exists an X from here, such that for all U over here, some proposition alpha is satisfied. And the morphisms are kind of a bit funny looking, so you can write it down in a diagram, but maybe it's more immediate to see in this kind of a bit informal type theoretic notation. So we have some forward part going from going between the bases in the expected forward direction, but then we have this backward part here, going from a re-indexing of V over here to U. And then we have a certain implication, and this implication is exactly, it makes use of these forward-backward functions downstairs, and it's exactly modeled according to the interpretation of the implication in the original dialectica translation. So to introduce this parameter that I mentioned about these maps with respect to which we want to complete to, we're looking at display maps. So those are essentially maps with some closure properties in the base category, especially they're pullback stable, and I want to indicate that some map is a display map with this double-headed right arrow here. And we can, in particular, look at the full subfibration of the codomain fibration if the base has pullbacks that has as objects only those arrows from the display map class, and as morphisms, all squares with the remaining arrows can be freely chosen. And the dialectica fibration now is a construction that goes as follows. So given a quotient decalibration over such a display map category, the total category is defined in kind of a similar way as we have seen in the slide before. There's some additional dependence here at the bottom going on. And also you might have noticed here I'm not looking at sub-objects anymore, but actually, because I started with an arbitrary fibration, those kind of propositions now are really just points in the fiber over the domain of this composite here. So that's how the kind of dependent generalization goes. And we get the fibration by projecting to the very first component from this total category. And from this you can, in a canonical way, recover the traditional dialectica category So this fibration is bicomplete in the sense that it possesses fiber co-products and products, and it actually arises by iterating these completions, but it's not the sort of simultaneous free bicompletion, so this kind of mismatch you can see, for instance, discussed in this paper by Bosta. So what are fiber co-products in a fibration? So the idea is that the co-product operation should come from left adjoint to reindexing. So we want our fibration to be an op fibration in particular, but this sum operation should cohere with reindexing in the sense that what's called a Beck-Chevalier condition is satisfied, which is a condition that gives a sort of canonical commutation between these processes. Now there is an important construction called the family fibration. And so this is done by taking a pullback and then post-composing with codomain map, and that in particular, if you plug in a fibration, gives you in a free way a fibration with fiber co-products. The property this definition can be motivated from sort of the discrete case where the base is set, and then that would be exactly a fibration way to say that the original category has set index co-products. So we also want exponentials to exist, or dependent products, and for those we look at we want our class of display maps to be closed under dependent products. So this is just taking place completely in the base right now. This notion essentially is like a dependent generalization it's a dependent generalization from just the usual Cartesian closure. Then the fibrational version can be defined sort of in a dual way using the dual fibration, which is a way of dualizing a fibration fiber-wise. So fibration has fiber products if and only if its opposite fibration has all fiber co-products, and then analogously the fiber product completion arises as the opposite of the co-product completion of the opposite of the original fibration. So it turns out that actually the dialectica construction can be described as the iteration of first taking the completion with respect to the fiber products and then with respect to the fiber sums, and that kind of pays tribute in a precise sense to that name dialectica fibration, because we want to have as outputs of the dialectica interpretation formulas of the form there exists, such that for all, such that some formula holds, and this sigma pi sequence is exactly the categorification of this. And also, this is already what some people would call the polynomials in the fibration, so there is like an ongoing theme with polynomial functors, which I'm not going to talk about, but there's plenty of stuff to think about there. So to get to the point of this alternative description for these completions, we want to introduce or rather generalize this previous notion of Gödel fibration in the non-dependent sense. And basically the idea is that such a fibration is one where you can always bring elements into the appropriate format. So first of all, we have to say what quantifier freeness should mean. So there's some proof theoretic way to say this, and our categorical definition is a translation of that. Furthermore, we want the quantifier free elements to be stable under substitution, because that makes sense logically. And furthermore, we also want every formula to be equivalent to quantifier-free formula. And the notion that we're considering is a direct generalization of the previous groundwork that Matteo, Davide, and Valeria did. So they considered the case of product projection maps in a fibration where you can kind of relatively explicitly do certain commutations, but here we're really working with an arbitrary display map, so these product and co-product operations are just the Cartesian and co-Cartesian transports or something even more abstract. So basically, just to illuminate a little bit on this definition, so the prior way to, the preconception was that a formula should be quantifier-free if it satisfies the following property. So assuming we have a proof pi of a statement of the form there exists I, beta I, assuming alpha, that's not in the slide, I forgot to write that. Then there exists a witness T, which depends on this given proof T, together with the proof of beta of that witness. So it's kind of the way you extract some, you are able to extract some witness, so it's kind of a rather strong property. And that's something that we can see here by saying, okay, an object alpha and some fibers quantifier-free the following holes. So for any other object in some other fiber, together with the vertical map from this one object to the co-Cartesian transport over some map in the base, there uniquely exists the following data. So first of all, a section G of this arrow in the base, so that's like extracting this witness, and also a vertical arrow, which is like this implication, which fits into this square here. Analyzing this has to do with, how those maps relate to each other using the structure of the fibration. And then the actual quantifier-free, so that's the notion of the quantifier splitting, and then quantifier-freeness means that this process of splitting is that we can do the splitting sort of stably under pullback, and in particular we want to have this covering property. We want enough quantifier-free elements to exist. So the first important notion is that of a Skolem fibration. So Skolemization means making effective a witness. So if we have a formula for all x exists y such that pi of x y holes, we want to be able to say, well, I can actually make this effective by introducing a higher order function that keeps track of this y, and sort of inspired by this, we look at this notion of dependent Skolem fibration, in which it's sufficiently complete and enough of these quantifier-free elements exist, and furthermore, the co-product quantifier-free elements are stable under products. And it turns out that this gives a sufficient categorification of this Skolem principle, which is expressed by like an isomorphism, where you replace the quantifiers and the substitution by the corresponding transport maps from the tri-fibrational structure. And then to get the notion of a dependent Gödel fibration, what we want is this additional property that we can bring any formula in this kind of pre-next normal quantifier-free form. So we need an additional property for that, which involves the co-product quantifier-free elements having enough product quantifier-free elements themselves, which gives you some idea of how all this alternation between sigma and pi comes into play here. And then the main results that we're working towards at the moment is an internal characterization of the sum completion in that vein by exactly the condition to have enough co-product quantifier-free elements, and hence also the dual version for the product completion. And then finally, the equivalence that given a bicomplete fibration in that sense, then this is an instance of the dialectical construction of some other fibration. This is exactly the case if and only if the fibration is a dependent Gödel fibration in that sense. So thanks for your attention.
Thank you very much. We have time for a few questions.
Thank you for the wonderful talk, Jonathan. I was wondering if you could say a little more about the relation to poly from your slide where dielectric B is the sum of the product of completion of B.
So I think at least in Tamara's and Blaine's thesis, this sigma f pi f dialectica is exactly, like as a fibration, is exactly the fibration of f polynomials in a given fibration. I'm happy to chat more about this, and I'm happy to learn more about this, but I don't myself have a good grasp on this poly landscape, so that's the best I can do for now.
So you say you're working towards these results. How close are you to actually having proved them?
Not too far, so it's...
You're confident they're true?
Yeah, I think so, yeah. Modulo maybe some slight adjustments of some auxiliary definitions, but I don't think there's a problem.
Any more questions?